Hello, everyone. This is Professor Ma, and this is the summary on the sections on tangent planes and total differentials. Uh, we have a conditions that for a point that's smooth on a surface at a point, if the partial derivatives is defined around a neighborhood around that point and are continuous. And basically all elementary functions satisfy these conditions. If you're at the point P, if the elementary functions define around a neighborhood, a small neighborhood of that point, then this condition fits. So we restrict ourselves to this type of functions. And so assume that we have a point that's smooth on the surface, then we would like to obtain the tangent plane. In order to get a tangent plane, I need to get a normal vector for the tangent plane. And then we get a normal vectors as we look at the partial x, and that's going to give us the slope. And of course, if partial x is equal to m, and then on the cross sections of the plane y equal to a constant, I have these 1 to m ratios of these vectors, the directional vectors on the plane. But if I were to put these directional vectors into three-dimensional space, and they will be in the standard positions, then the y components will be 0. In other words, the directional vectors in a three-dimensional directional vector, that is the vector 1, 0, m. Similarly, in the y directions, we have the partial derivative, suppose of y is equal to L, then similarly the vectors 0, 1, L sits in the x-plane is the directional vectors for the tangent line. And these two lines, these two tangent in x direction, in y direction, these two vectors sits on the tangent plane. So we take the cross product, we get a normal. If we cross in this order, the 0, 1, L cross 1, 0, M in this order, then the normal we get is normal that point downward, because we will get the z component equal to -1 if you take the cross product, check it. And on the pictures, it looks like these. And I have two directional vector came from the partial derivatives. I cross it and I obtain the normal vector. In this case, it points inward toward the center of this sphere or globe, whatever it is. And we can write on the equations, and this is the equation for having the normal and base at the point P. So this is the general equation for the tangent plane at a point on the surface. Here's examples. We'll calculate the derivatives, and we'll calculate the derivatives in the x directions, partial x, partial y, and substitute the 0.23, so we get the number for m and l. And then voila, then cross them, then we already did mLs, we just put that into the equations from the formulas at the base 0.236, and that's the equations. I'll leave it to you to visualize this. This is the formula is a sphere, semi-sphere with radius 7, and this the point sits on that sphere in the first octant. You can look at it to justify that this is reasonable as a tangent plane at the 0.236. What else can we use it for tangent plane for? We can use it to approximate. Remember in the case where we have one variable y equal to f of x, and we have tangent line, and suppose I'm at a point at point A, and I move over a little bit, and so the dx, which is the same as delta x, I want to find out what is the function value at f of this, f of a plus dx. But the easier thing to do, of course, is instead of finding what this value is, we're going to proceed to find out all the way to the tangent line. And the way we do it is doing by looking at the difference between the y and between the two y values at a and a plus delta dx. And this is easy to calculate because this is equal to the slope times dx, whatever the slope of the tangent is. And once I calculate this, this is equal to f prime of a times dx. Then I add it to the amount f of a, add them together, and this will give me the total estimations of the function values up to here. So these are estimations. So in other words, it's easy for me to calculate that little red piece right here. And that is this formula for approximation on a line using tangent line. We do the same thing with tangent plane on the surface. Okay. And suppose I have a surface and I'm a point, base point at A, B, and I'm going to go along the x directions, a small amount dx. I'm going to go along the y direction, a small amount dy, and wind up at a point a plus dx, b plus dy. And the question is, suppose now I have a plane that sits over, that contain the point A, B, C, and suppose this plane sits in the space in such a manner, the slope in the x directions of this line, the slope is m, but from this side, in the YZ side, the slope of this is L. And the question is, if I were to go from here all the way up to that point, what's the amount of gain in Z, dz equal to what? And if you think about it, it's very easy because this basically to go from this point up to that point, I need to go along this face of this box or in XZ plane, then I'll go along the face in the YZ plane, turn a 90 degree and go along the other side of this building, if you like. And altogether, the change is going to be, first of all, if I go from here to here, the rise is going to be the slope m times dx. And that's, of course, is equal to that, it's same as that. Then I'm going to go from here, then go up, and then the gain is going to be L times dy. So altogether, the gain is the sum of those two. And this we call the dz, the sum of this height gain in two different perpendicular directions is the total gain. We call this a total differentials. Okay. Which, yes, this is the total differential. Here's an example how to calculate the total differentials. Here it is. And here's the examples. And so we are based at a point in XY coordinate. We are based at a point 1, 3. And we want to estimate as we change our positions and move over to the point 1.03, 2.94, what is the change in the function values. So if I move from 1.3 to this point, the amount of dx is going to be 0.03. And then I go down to 2.94, and that's the dy is going to be minus 0.06. So the question is, if I move from 1.3 to this point, on the tangent plane, where will I be? What's the total change in the amount of z's on the tangent plane? So first I calculate the slope at the point 1, 2, 1, 3, and in the x and y directions, plugging at the point 1, 3 in x direction is minus 9. The slope in the y direction calculates minus 5. And then multiply the dx, dy respectively to the slope, m times dx, l times dy, and that's a total change in the z. So I get the total differential to be change is that much, 0.03 from the original output at 1.3. The original output 1.3 is minus 6, so plus the change. So so the approximate value we arrive at is minus 5.97. If you type in the calculator, you get fairly close. So it's a good approximation. So that's what the tangent plane is good for these total differential approximations. Okay, that's it, and see you next time. Bye-bye.